Hi, thanks for tuning into this video where we will be learning about quantum numbers and electric spin. So these four quantum numbers right here are the way that we describe the location and the state of an electron in an atom. So before we get started talking about the individual quantum numbers, I want to define the term orbital for you. So an orbital is the region of space where an electron is most likely to be found. So if this is our atom right here, let's say this is our nucleus, the electron can be found anywhere here, and so this would be the orbital. And so you can think of it as almost like a probability cloud. So let's get started on our quantum numbers then. So the first quantum number is called the principal quantum number, and it is symbolized by the letter n. So n can be any positive integer starting with 1. So it can be 1, 2, 3, and so on and so forth. And n indicates the main energy level that the electron is occupying. So if this is our nucleus, and I know it's kind of ugly, so bear with me, these are the energy levels then that the electrons can be occupying. So you have n equals 1, n equals 2, n equals 3, and then again, it can go on all the way up until who knows what number. So these are also known as shells, and electrons can be found in these shells. So we know that since electrons are both particles and waves, let's talk about how electrons can orbit in these different energy levels. So as the electron travels around the nucleus, and these energy levels, if you can picture it, go all the way around the nucleus. As the electron travels around the orbit of the nucleus, it travels like a wave, and the length of the path is an integer number of wavelengths. So if this is the path that the electron takes, for n equals 1, it's going to be 1 wavelength. And that's a standard rule throughout. So the orbit that the electron is taking is equal to, for n equals 1, 1 lambda, for n equals 2, 2 lambda, for n equals 3, 3 lambda, and it goes on. So because for n equals 1, because it's limited to 1 wavelength, the electron is really limited in what it can do. So as we can see here, it only can do this. And meaning it can only go around the nucleus in a circle, which leads us into the second quantum number then, our angular momentum quantum number. And it is symbolized by the letter L. So L indicates the shape of the orbital that is created when the L indicates the shape of the orbital that is created by the wavelength the electron is orbiting in. So values for L are dependent on values for n, and our L values can range from 0 up until n minus 1. So for n equals 1, our L value, the only possible L value is 0. For n equals 2, the possible L values are L equals 0 and 1. So when L equals 0, then we have a specific shape of an orbital that is specific to L equals 0. And this orbital is called an s orbital. When L equals 1, again, another specific orbital called a p orbital. And so these letters correspond to shapes of orbitals. So an s orbital is the shape of a sphere. It's kind of a bad sphere. And the p orbital is the shape of like an infinity sign or a dumbbell. And these right here then are called subshells. So notice that the number of values for L is equal to the value for n. So when n equals 2, we have 2 possible L values. Moving on to our third quantum number, we have our magnetic quantum number, symbolized by m sub L. And when we apply a magnetic field on an atom, the electron can exist in different magnetic states that's associated with the orbit of the electron. And that's what our m sub L is quantizing. So the values for m sub L depend on the values of L. So possible m sub L values range from negative L to positive L. So when n equals 1, we know that L is going to equal 0, and so the only possible value for m sub L is 0. I'm going to use the same notation. So when n equals 2, we know that L is equal to 0 and 1, And so possible m sub L values include -1, 0, and +1. Because there's only one m sub L value here for n equals 1, there's only one orientation along the XYZ axis. And I'll explain more about the XYZ axis in a second. But the XYZ axis it shows pictures in 3D. So this is our X, our Y, and our Z. So for m sub L, there's only one value, there's only one orientation along this axis, and it is a spherical orientation. So think of this in 3D, it's a sphere instead of a circle. And so when we apply that magnetic field on an atom, the electron can exist in different magnetic states here. Now for m sub L, we have 3 values. So there are 3 possible orientations along the XYZ axis. So our first orientation would be this up and down, and the electron can exist anywhere here. Our second one would be our sideways, and then again, the electron can be anywhere here. And then our third one would be this diagonal. And so again, the electron can exist anywhere here. And so we can picture it. Let's say this is our nucleus here, and the electron is orbiting around the nucleus. That's this path that we were talking about, just in the actual shape of it. And so we can picture these as moments anywhere here on this orbit. So it can exist like this. It can exist like this. And it can exist like this. And so depending on the magnetic state of the electron, it can orbit in any of these ways. And that brings us to our last quantum number, which is our spin quantum number, and it is symbolized by m sub s. And our spin quantum number makes you kind of think that the electron is spinning on an axis, like right to left, and that's not necessarily the case. So let's draw the electron here on its axes. And so we can the spin quantum numbers are labeled as spin up or spin down. And so we label these by a +1/2 for spin up and a -1/2 for spin down. So no two electrons can have the same 4 quantum numbers, which is how these numbers can explain the location of all of the electrons in an atom. So let's do a practice problem now of describing an electron using these 4 quantum numbers. So if we have an electron that is in n equals 3, let's say it's right here in the 3rd energy level, we know that possible values for L, if we look up here, are 0 up until n minus 1. So we can have 0, 1, and 2. Now we look at our 3rd quantum number, which is our magnetic quantum number, and so possible values for m sub L include -2, -1, 0, +1, +2. And now our spin quantum number, our m sub s, can only be +1/2 or -1/2. And this is how you would use the 4 quantum numbers to explain the location of an electron inside of an atom. Thanks for tuning in. Watch next week to see what other physics concepts I can try to explain, but probably not do very well at. Thank you.